Hi everyone and welcome to this new video. In this video I want to introduce a new series of videos, and in this new series the objective will be to analyze, to do some initial usage of various tools. So these are like extremely useful and foundational tools that you will end up using one time or another. In this first video of the series I wanted to introduce the tool GDB, which is the GNU Project Debugger. It is an open source debugger that in Linux you will most certainly have used at least one time or even more, and that in the future will probably use it at some point in time. So in this video I want to go over through installation, basic commands, documentation, how to use the debugger. So the debugger essentially is the one we see here on the right. This is one command that allows us to disassemble a simple C program. So here you can see the C instruction, and here you can see the relative assembly instruction that implement that C code. And so with the debugger, we can essentially check the control flow, we can check the memory, the registers. I will talk about extensions to GDB, because basic GDB can be very bare bones, so it's very foundational, but you can extend it with various things. So this is the content for this video. I hope it is useful, I hope it is interesting. If it is so, please leave some feedback, subscribe to the channel, help me grow here on YouTube, and in general, let me know what you think and share this video with like-minded people. Having said all of that, we can now start with the content. So first things first, let's talk about installation. Given that we are in Linux operating system, you will use a Linux distribution, therefore you will probably have an appropriate package manager. For example, here I am in Arch, so I install with the pacman package manager. If I am in Kali, Ubuntu or Debian, I'm gonna use the apt package manager. The idea though is that since GDB is a foundational tool, you will find the binaries, you will find for every distribution the relative binaries for the program. So just use the typical package manager you use and install the package called GDB and it should work. In my case, as said, I use Arch Linux, so the command was pacman-s gdb to install the GDB program, and sudo because pacman requires sudo. So now that we have installed the program, how can we use it? What are the basic commands? Well, essentially, first of all, I'm gonna show a simple C code. So here is a simple C code. I'm gonna remove this. So here we have this simple 1.c. I open this and it contains an extremely simple program with a main function and an example function. The main function prints hello world and then calls the example function with the argument a string test. And the example function just sets a variable and returns that variable, and before returning the variable prints out the string with the format string %s. So really not much to it. To compile this program, we can do gcc, name of the program, -o to specify the output name. Now if we do it just like this, we are not inserting any debugging information, which can be useful when using tools such as GDB. Now with this simple program, with this simple execution, we can already see the elf binary created. So we can execute it. It's gonna say hello world and test. And this is an elf binary. So like notice this, it says elf 64-bit by executable. Now, anytime we have an executable elf binary, essentially we can use GDB on top of this elf binary. How? We just do GDB and then the name of the binary, so the path of the binary. In this case, I have to put a // because I have to say from the current directory extract the simple one binary. I do this and I get all this initial output, all this initial thing about the license. Now, since I'm not interested in that because I already read it, to not show that initial text, I use the flag -q to be a quiet mode sort of. So it starts like this. It says reading symbols from simple one, and then it says this GDB supports auto downloading debug info from the following URLs. Enable debug info D for this session, and I say no, we will not use debug info D. Why? Because essentially debug info D is a mechanism, is an API that was introduced later on in order to debug things like the standard C library and common projects, where if you actually want to have the debug symbols, you would have to compile your own version of the C standard library, which is glibc in Linux. So it is called glibc. To debug this library, you would have to do your own debug version compilation. Now, since we're not interested in that, since doing a debug version compilation can be time consuming and stuff like that, they introduced this debug infod to allow you to not have the debug version installed on your system. Rather, there is an API which abstracts away the need for having the debug version. But in this video, it's an introduction to GDB, so we are not really interested in that. We are more simple, like simple stuff for this video. Later on, maybe I can do more videos on GDB if you're interested like on this topic. Now, one of the first things we can do is we can extract information about the functions that are included in the binary, and we can do that with the command info functions. And it says all defined functions, non-debugging symbol, we have main, we have example, we have start, we have puts, we have init, and we have fini. So we have a bunch of non-debugging symbols. Now it says non-debugging symbols because these symbols are actually used by the program itself. So notice that we have main and example, and here it gives us an address where these functions live. This is not the final address, this is just the static address of the elf structure. Let's say that we want to disassemble a function. And when I say disassemble, so here the word disassemble essentially means we want to read the assembly code, the assembly instructions that are executed by the CPU. Because when I have a program written in C, the CPU is not able to execute C directly. So I have a compiler such as GCC, which allows me to go from C to like an assembly. In this case, it's x64 86 assembly, which means that these are instructions that an Intel CPU can execute. So these are instructions offered by the ISA of the Intel CPU, which is the set of instructions that the Intel CPU is able to execute them. So to read this instruction, we do disassemble and then the name of the function, in this case main. I think it's disassemble main. Okay, so the correct command is disassemble main. And notice here we have this instruction like push RBP, move RSP RBP, lea, move call lea, move call move pop ret. So these are the instructions that the Intel CPU will execute. Now there are different ways of representing this instruction. In particular, there are two main syntaxes, which is the Intel syntax and the AT&T syntax. Now to change the syntax, you can use these directories, these directives, set disassembly Intel, set disassembly AT. In this case, this is the AT&T disassembly. And you can notice this because, for example, here are the registers like RBP, RSP, RAX, and they have the percentage sign. So this is like a sign that it's AT&T. I actually like to work with the Intel one. So like I'm just going to set disassembly Intel and then I do it again. And notice now that the code change. So we have push RBP, move RBP, RSP. Notice, for example, that the order of the operands is flipped between the AT&T and the Intel. In the Intel, we have that the destination is the first and the source is the second. So in this case, this move instruction would move the current value of RSP into RBP, while in the AT&T is actually the opposite. The first one is the source and the second is the destination. I mean, it doesn't change much, it's just remember this difference because it's really important. So this is the idea. Now in reality, if you want a little bit more of info, the CPU does not actually execute this instruction like push, move, lea, call and stuff like that. Because actually there's microcode. So the CPU internally implements these instructions with other smaller instructions called CPU microcode. So the flow is the C program is compiled into assembly, and the assembly is compiled into micro instruction. So it's like micro instruction, microcode essentially. This is assembly code, this is the source code we could say, then we have assembly code and then we have microcode. But we don't really care about that because microcode is internal to the CPU. there are some cool research about microcode, but for what we need, we just can abstract away the microcode and we can say, look, the CPU allows us to execute these instructions, and with GDB, we can analyze this instruction with the command disassembly, and we can change the syntax with Intel or AT&T. Now, suppose that I want to show the source code and then the relative assembly instruction. How do I do that? Well, there is this command, disassemble /s main, that works as follows. Now, notice that nothing changed. Now, nothing changed because this program was not compiled with debug information. Because if you remember well, when I compile this program, I'm gonna exit from GDB with exit. When I compile this program, I just did gcc simple1.c -o. To actually put the debug information, you have to do -ggdb. And with this, you are inserting debug information that the GDB is able to read and process. Now, let's see what changed. First of all, we can do a simple test. Let's do simple2 with the debug information and simple1 and simple1 without. So simple1 without, simple2 with debug information. Notice, of course, that the simple2 with the debug information is a little bit heavier in size, which makes sense because we have added something else. Now let's try to debug the simple2 command. I mean, they are the same source code. It's just that in simple2, I also added debug information. And notice here it says, reading symbol from simple2. If instead I do the same thing here with simple1, it says this debug info D, and it says essentially no debugging symbol found in simple1. So it says no debugging symbol because we did not put them. So GDB tells us if we found the debugging symbol. Now let's do the command info functions here and info function here. Now notice the difference. In the file with the debug information, it tells us that this function example and main, it tells us the signature of the function and where they are defined, in which file, for example, simple1.c. In this other, in which we have no debug information, they are all merged together as non-debugging symbol. Now in this case, these are non-debugging symbol because this symbol belong to like the environment that allows us execution. It's not our specific code that we need to debug. This has to do with the environment. If we want to debug this, we need a more complex setup, which we're not interested right now. So this is how having debug information can help the debugging process. Now let's back to the previous command, disassemble /s main, and disassemble here /s main. If I do it in the non-debug version, I simply get the code, the normal assembly code. Also, let's put in both the Intel syntax, because I prefer like that. Intel syntax, perfect. So disassemble here, and then I say, I take this and I'm gonna execute it on the other. Now notice how it changed in the version with the debug info. Now we have the source code in the main and then the relative assembly code that implements that source code instruction. For example, we have a printf, and here is the assembly that deals with that printf. In this case, dealing with a printf means calling the function puts at the PLT and preparing the arguments in the registers. Calling the function example is about calling example and preparing the arguments in the register, and so on and so forth. In this case, I do not have all this information because there are no debugging info. So from now on, I'm gonna assume to work with the debug version, so we will not compare all the time, but the idea is that when you want to debug, always put the debugging symbol. And of course, if instead you're trying to do reverse engineering, well, that is a different thing, because you're trying to understand a program that maybe the developer do not want you to understand. In that case, GDB is not too useful. You need tools like Ghidra or IDA because you need to do something else. GDB is useful when you have the debugging symbol and when you know the program you're trying to debug, essentially, most of the time. So we can then work with the text user interface, the textual user interface, also known as TUI. How? Well, we can say TUI enable, and this is gonna give us the like the view of the source code, and then we can have TUI layout. We can say, for example, if I want to see the assembly code, I can say layout asm, and I get back to the assembly code, or I can get back to the source code with TUI layout source. So I can swap between the assembly and the source code, and then finally I can say TUI layout split to have both the source code and the assembly code. And this TUI layout is useful when you need to debug and you want to quickly understand where you are visually in the source code. This is extremely useful. When working with the TUI, sometimes things break visually, so to refresh the screen, you simply do a Control L with the lowercase l, and it's gonna refresh everything so that it makes more sense. So this is just some tips. We will keep using the TUI throughout. So in terms of documentation, the thing is that GDB contains a lot of commands, like 1,000 or even more commands. So to understand what each command do, in this video we'll showcase some, but not all. So to understand what they do, you can use the internal documentation helpers, which are help and apropos. Now the help command works when you give it a specific command, like we say help TUI, and it lists essentially all the commands that you can use with TUI. So you can say TUI enable to enable the TUI, or TUI disable to disable the TUI, or TUI focus, FS, focus, layout, TUI new layout, TUI refresh, TUI reg, TUI windows, and stuff like that. So you can have a bunch of different things regarding the TUI command. If instead you don't know exactly like the specific name of the command, but you know sort of like a bunch of structure, like for example, it's called, it's like, I don't know, TUI window. I don't remember TUI window, but I remember that there is TUI WI, something like that. I can use apropos with this thing. Actually, I think it's without. And essentially, it shows me all the things that match this kind of regex in a way. So TUI. In this case, it also gets TUI because I think I mentioned TUI and TUI window and stuff like that. So this is the idea for the documentation. Is extremely useful when you want to learn a new tool. You just take your time, you understand the specific task that you need to do with that tool. For example, in this case, it's debugging, and then you learn about if the tool has internal documentation. In this case, GDB does, so use that when you forget something and you need a quick reference. So of course, why do we use a debugger? We use a debugger to step through the source code, to analyze the state of the program during its execution, to stop the program at certain times and then understand the state and then move forward manually one step at a time. Now to do that, we need to set breakpoints. Essentially, the idea is that breakpoints allows us to stop the program, so like it executes normally, then we meet a breakpoint and we completely stop the program, we halt the program, and then we can have control of the state of the program. So how do we set, for example, let's see, I'm not sure how I can clear it, I don't know. It doesn't work clear, so I guess there must be some command to clear, maybe, I don't know. Anyways, to set the breakpoint, we can do break, so we can do B, or you can also do break, but let's just write B, and then we can put the name of the function, like in this case, break main. It's gonna break at the main function. So notice here, we put breakpoint 1, and here is where the breakpoint was inserted. Notice that it was not inserted in the truly first instruction of main. Why is this the case? Because the first two instructions, these are called the prologue of a function, and essentially they have to do with setting up the data structure used to handle that function, which is the stack. So this prologue, I'm not sure if it's written like that, essentially it sets up the frame, the stack frame for main, It creates space in the stack memory area. We will talk about this in a later video, but essentially is that these two functions are just set up for the actual function, and the first true instruction of the function is this one. So now we set a breakpoint. Then to list out all the breakpoints, we can say info breakpoints, and notice here it says, look, you have a breakpoint at main. So let's do it again because it did not really work. So we say info breakpoints. So we say, look, you have one breakpoint at this particular address in the main function in this file at line 12, because in the terms of source code, this is line 12. So when you put the debugging information, he is able to map assembly instruction with source code lines, which is extremely useful when you want to debug. So you can also do info break, it tells you the same exact information, and also IB, because GDB commands can be shortened as long as they are unambiguous. In this case, info breakpoints is the only command that starts with an I and then with a B, so where the first word starts with an I and the second with a B, so you can use just IB for info breakpoint. Now, once we put a breakpoint, of course, we want to run the program, so we want to execute it. And to execute the program, we can just say run. So we say run and it's gonna start the program normally. Now, of course, it says starting the program and then it asks for debug info D. We don't really care about this right now, so we can just say no. Then it started the program and then it said, look, I met the breakpoint at this particular line and now I stopped executing. So at this point, we have full control over the program. This means we can analyze the memory, which we will see later, we can analyze the registers, which we will see later, and we can analyze the control flow of the program. In particular, there are a bunch of different instructions to like step up, step on the control flow in a controlled way. So what do I mean with that? For example, if we use C, C stands for continue. It means continue execution until either the program ends or you meet another breakpoint. So it's sort of like, okay, you just keep going forward until you can. So if you do just a C, since we have no other breakpoints, we're just gonna finish the program. So I do C, look at this now, the UI is kind of broken, so I have to do Ctrl L to fix it, but essentially it printed information and then it stopped executing. So if I say run again, and then I say C, it prints hello world and test. This kind of breaks the TUI because the lines are broken. If I do Ctrl L, I'm not gonna see anymore the output of the program. So this is a little bit broken, but anyways, so that's essentially the general idea. And then I can sort of like, okay, in this case, it exited because there's nothing else to do for this particular flow. Now let's say instead that I want to sort of like break the program, but then I don't want to continue until the next breakpoint or until it finishes. I want to step one instruction at a time. How can I do it? There are two main ways to do this, which is the N and the S. Now the N is gonna be jump to the next source instruction. So if I do N, in this case, it's gonna jump to the example call here, to the example call. Notice here, before I was in 12, print hello, and then I'm in example test. So this is the N. It means that I did not jump one assembly instruction. I jump one source code instruction, which can mean many assembly instructions. And indeed, initially I was in this instruction, notice with this address, with main plus 4, and then now I jumped here. So I jumped 1, 2, and 3 assembly instructions. So this is something. Then we can continue and then we can run to get back at our original point. So another thing we can do is jump to the next instruction, but the assembly level. So NI, we do next ASM instruction, next assembly instruction. So look, in this case, I will go from main plus 4 to main plus 11. So NI, and I do main plus 11, I'm in the move instruction. I can repeat it again, I can repeat it again, I can repeat it again. Of course, this is gonna print hello world, so it kinda broke the TUI, gonna have to refresh. But essentially, like this, I can just move one instruction at a time. And at some point, I am like in libc code, so like, and then I exit the program. So that's the general idea. So I do run again, and I get back to the main function. Now, if you notice here, I put next ASM and source instruction and then step ASM and source instruction. Why? This is interesting because sometimes instructions are calls to other functions. Like for example, consider this call to example and consider the source code here up. Like in this source code, when I do example test, this example actually expands to this code. So sometimes I don't want to just go to the next instruction and ignore the call. I actually want to go inside the call to understand what the code is doing there. Not in this put, but essentially it's in the example call, So how can I do that? So like here, It's in the example code. Now, how can I do that? Well, the idea is that I'm going to do next I a bunch of times until I get to the call. Let's see here, until I get to the call instruction. Perfect. At this point, I do not do ni. I just do si. So like jump into the example code. I jump into the example code and notice now I am into the example function. So again, once again, deal with this particular code. Notice here down that I get the name of the function and the value of the argument test. So this is interesting. Then I do next I, next I, next I, next I, next I. Like I do all this stuff, and then I can sort of like analyze the behavior of this function. So when I say next instruction, it does not go internally into calls, but when I do step, it goes internally into calls. And for step, the same thing applies on the difference between ASM and source instruction. So essentially, that's the idea. So let's say that I want to, so like I have my breakpoints here, but let's say that I want to remove them. I want to remove them because I don't care about them anymore. I can say either clear. Clear removes the breakpoint at the particular line. I can say del, and I can say the number of the breakpoint. So in this case, it's 1. And I say, look, there's no breakpoint anymore. No breakpoint anymore. If I do run, I'm not gonna even stop at a breakpoint because essentially there is no breakpoint anymore. If I have break main and break example, I do run, I'm at main, I do continue, I get into the example because this is the second breakpoint. And essentially here I have also the argument test. And if I do info break, I'm gonna have 2 and 3 breakpoints. So like I'm gonna have 2 breakpoints, but they have number 2 and 3. I do del 2 and del 2 and del 3, and I've removed all the breakpoint. If I do run again, notice once again I just print out hello world and test. So that's the general idea. Now let's put once again a break in the main. So break main and run. Something I didn't mention, but GDB allows you to write one command, for example, next I, so next ASM instruction. If you want to repeat the command, you do not have to write it all the time. You can just press enter. If you press enter, essentially the same command as the previous one is going to be executed. So in this case, it's just going to do ni all the time that I press enter. This can be useful when you have to press it multiple times. So this is just a little thing to consider. And so this covers an introduction to breakpoints and control flow and how you can handle control flow with GDB. Essentially, you can handle it by putting a breakpoint, by listing out the breakpoints, by running the program, and by continuing execution as you want with continue, next instruction or step instruction, and by considering the difference between stepping to the next assembly or to the next source, both in next and step, and then you can remove the breakpoints. In terms of how you can set breakpoints, there are various syntaxes you can use essentially. So for example, let's say that I want to, let's disable the TUI for now, and let's analyze the example call. So for example, let's say that I want to put a breakpoint into this, this instruction. The way I can do it is I can do breakpoint, I can do this star vulnerable plus 26. So of course, in this case, it says, because there's no symbol vulnerable, because it's called example, actually, the function. And so essentially now, if I disassemble it again, it says, actually here it does not say, but if I run it, I'm gonna have, this is the breakpoint at main, and this is the breakpoint at at simple one in example at this address. So this address essentially is plus 26. So just notice the address at which we are breaking here. This is it, which is plus 26. So this example showcases that you do not need to know the address, the specific address. You can just do with offsets. You can say, starting from the start of the example function, move to plus 26. And GDB shows this plus 0, plus 1, plus 4, plus 8. This is useful because each instruction has its own size, which is variable, it's not always the same. So you might get confused about what's the specific address. Just look at the numbers and use those to put breakpoints. So essentially, this is the idea. Now, of course, remember that what I showed with respect to the control flow management is just the most simple stuff. There's much more complex ways to use this kind of mechanism. For example, GDB offers the ability to stop only when certain conditions arise. So just read the documentation, just depending on your need. I'm gonna put some link in the description below, so just know this. So another extremely important thing is to analyze the registered values and the memory. This is because the CPU, while it executes its own instruction, it uses both registers as memories where you can put stuff, and also the memory. So we need ways to understand both of these components, because the instruction and the control flow is handled by the CPU, of course, but the CPU needs to save data into registers and memory. So we're gonna need to understand how to read registers and memory. Now, let's say that so let's run the program. So let's run the program, and let's say that we want to show the registers value. So here we have a breakpoint. So to show the registers value, we can do info registers. So info registers, and here I have all the registers value, RAX, RBX, R6, RDX. Notice that this is an x64 CPU, it's an Intel CPU, which means that in this architecture, in the x64 architecture, these are the different registers that I have. R8, R9, R10, and so on and so forth. And these are the values in hexadecimal and in decimal. In this case, for some, in this case, it's not decimal. So like for some it's in decimal, for some it's not. So that's essentially the idea. So this is for the printing the registers. I can also do IR. IR is the same, info registers, essentially. Now, if I want to reference to a register value, I can do the dollar and register name. So for example, dollar and RAX. So for example, if I want to print out the value of RAX, I can do print slash the dollar RAX. It's gonna print me the value of RAX in hexadecimal value. If I want to like convert into hexadecimal, I can use this /x to convert into hexadecimal, /o to convert into octal, I think b to convert into not b, I think cells letter are meaningless, maybe I don't know, binary. How do I do it into binary? So to convert into binary is actually t, it's the t flag /t. So this is the binary value saved in the register. So this is the idea. And notice that every time I use this command, GDB creates new temporary variables like $1, $2, actually it's print $1, print $2, and so on and so forth. So it keeps creating these values, and with the print command you can just debug stuff, you can print out values, and so on and so forth. So this is for showing the registers and for using the registers. Then we can work with stack traces. So a stack trace essentially is all the functions that you call so far. So in an execution flow, you start from function 1, fun1, then you call function 2, then you call function 3, and this series of call taken together, when you put fun1 in the bottom, fun2 in the middle, and fun3 on top, this is called a stack frame. So essentially it represents the current, a stack trace, sorry. It represents the current execution, like how did you get to function 3? Well, you got call from function 2, which got call from function 1. So this is the idea. Now, for example, let's say that how many breakpoints we have. So del 4 and 5. Info break, no breakpoints. Let's put a breakpoint in example, and then let's run the program again. So in this case, we got into the example, right? So I'm interested to know how did I get here? And I can do a BT. So when I do a BT, it says, look, the latest function is example, the top of the stack trace, but the first one is main. So like from main, I got called into example, and notice this is an address, and if I disas main, I find this address that corresponds to the function after the call to example. So essentially this means when I'm done with example, I'm gonna continue execution from this address in main, because after I'm done with example, I'm gonna go back to main and execute this one, this move EAX 0x0. So this is extremely useful. Now, if you want to do a BT full, if you want to also show the local variables, you can do a BT full. When you do a BT full, for example, look at this. In example, we have res, which is 21,845, and then in main we have no locals. Now, why is this value so high? if in the program it was assigned to 1. And the idea is that if we do to enable, and if we just understand where we are in the code, so let's do to enable, and let's let's see, run. Let's run, and let's do this. The idea is that at this point, so beautiful, at this point, I still have to execute the instruction that initializes that particular local variable, which is exactly this move instruction, which puts the value 1 into this memory area, which is exactly the memory area of res. Indeed, if we just do next I, we have initialized the variable, and so the next time we do beautiful, this is actually equal to 1 now, because we have properly initialized it. And so with debugging like this, you can understand many memory errors, memory corruption errors. Now I don't need the 2 anymore. If, for example, you are working in a multi-threaded environment and you want to understand what all the threads are doing, you can do thread apply all bt or thread apply all bt full. It's like to execute it on every thread. In this case, we just have one thread with this thing, so it's all good. Now this where is used when something bad happens. It just shows essentially where you are in all the different functions. So once again, it can be useful. So, and this covers the stack traces, which allow you to understand, okay, how did you get into that function? What was the execution flow that allow you to get there? So extremely useful. Continuing, we have essentially the frame, the stack frame. Now, what is a stack frame? The idea is that every time you call a function, a stack frame is created, and this stack frame, you can think of this stack frame as sort of like a region in the memory, this stack frame, that contains all the local variables for that particular function. So if we have a simple function, like in simple1.cs, like look this function, it uses a local variable here, where this local variables is stored inside the stack frame, so that after the function is over, you can just eliminate the stack frame very fast using like pop and push mechanism, and you can get back to main, and this value is not valid anymore, essentially. So it's a really fast way to handle memory. Now, how do we print out this information? We can just write frame. It's gonna say essentially the frame we are working with, and we can move up or down one frame. So in this case, we can do, I think down, actually, I think up. So we can do one frame up, which is main, or one frame down, which is example. So we can move within frames. And so these are like basic commands to work with frame. Of course, if you're interested in that, you can just do apropos frame, and you can get all the things you can do with frame. Of course, there's a lot of things, so like just read what you need to do. It's a complex tool, but it's also extremely useful when you need to use it. Continuing, for example, we can list out the memory regions used by the file as follows with info file, essentially, info files. Notice here, there are a lot of memory regions which are mapped to the libc, to the standard C library. Then there is some supplied by the DSO system, and then we have like the internal, this internal one that are used internally by the ELF binary to do the various stuff. So for example, the data section, the got section, the got PLT, the BSS, the text, which contains the actual code, the read-only data, the GNU stuff, like there's a lot of memory region, and each of these region has a purpose. And by doing this, you can understand essentially the purpose for each reason. Now, so where we are right now, just let's do to enable. So we are within example, perfect. Now, if we want to examine directly the memory, we can use the x command. So we can do x, for example, this is x/32 wx, and then we put rsp. If we do this, we're gonna check the memory of the stack, starting from the top of the stack, going essentially down, which in this case is up in addresses. Now I'm not gonna talk too much about it because it's another topic essentially, but the idea is that this command, so let's try to read it more clearly. It says, look, I want to analyze memory. This X stands for I want to analyze memory. I want you to give me 32 of what? 32 words. So this W stands for words. It is essentially a size in terms of bytes. It means 4 bytes. So I want 32 blocks of 4 bytes each. And the final X here stands, and I want you to show them in hexadecimal format, starting from this given address. So this is the address we start with, which if we want to read it like explicitly, we can just say print RSP. So this is the address we start with. We can say 32XX from this address, and we get essentially the same as before. I can just disable the tool because we don't care about that right now. So this is the idea. Now, how we can change this? For example, we can say, just give me one word. Just give me one giant. So in this case, it's not one word anymore, but it's a block of 8 bytes. And I want them in hexadecimal format, or I want them, for example, in decimal format, or I want them in binary format, or I want them in octal format. So like you can change here 3 things, which is how many stuff you want, the first number, what size of stuff you want, and what representation you want to use for that stuff. So this is like a very simplified description. And the general syntax is like units, size of units, format of units, and starting location. Now the format types are like octal, hexadecimal, unsigned, binary, instruction, and string. The format size instead is a single byte, 2 bytes, 4 bytes, or 8 bytes. So this is called a single byte, this is called a half word, this is called a word, and this is called a giant. So for example, let's say that I want to print single bytes. Why? I don't know why, I'm just interested in single bytes. I say, give me 10 single bytes in hexadecimal format starting from this address. And notice what I got here. I got 10 different bytes because each row contains essentially, so we have 1, 2, 3, 4, 5, 6, 7, 8. Each row contains 8 bytes, so I have 8 plus 2, that's 10. Also, for example, let's say if I have 20, right? 20. Also, notice the representation it uses. Here on the left is the starting address, but the starting address is the starting address of the first element it shows us. It means that the element 0x01 lives in this particular address, which is 7FF, a bunch of Fs, and then E3B0. Now this one actually is not in this address, it is in this address plus the space required for the previous element, so plus 1 byte. So it means that this 00 byte lives in, I can just show you like this, 1bx, starting from this plus 1, so b1, so we have 0, 0. For example, if I want to check out this particular 55 byte, how much space do I have to go? I have to go the entire line here, which is 8 bytes, so I'm going to 8 here, but this 8 would bring me to this one, so then I have to add 2 more, so I have to go 8, 9, and then there is no 10 here because it's hexadecimal, so I have to say A. So if I do 8, I go here. If I do 9, I go to 6, 0. And if I go A, I go to 5, 5. And notice that here I got 5, 5. If I go 9 here, I'm gonna get 6, 0. Here I got 6, 0. So like this representation is extremely useful to become comfortable with because you will use it many times during, for example, binary exploitation. Now, to finish off the video, I finally want to talk about extensions. Now, because the idea is that over the years, GDB has been extended with different extensions. I mean, by itself, GDB, as I said, is a pretty foundational tool. It means that it's pretty bare bones with the functionality and the feature that it gives you. It's very powerful, but it needs sort of like a wrapper to work properly, to be more smooth, to be more efficient, and so on and so forth. So the idea is that GDB allows for extension, and various extensions have been developed over the years. In particular, here I mentioned two, which is PEDA, Python Exploit Development Assistance for GDB, and Pwndbg, Exploit Development and Reverse Engineering with GDB Made Easy. Now in this video I will showcase how you can work with Pwndbg. It's actually pretty simple. You clone the directory, you go into the directory and you do the setup script. You execute the setup script. It's gonna use Python and a bunch of other tools to like extend GDB with rich functionality, and then after all it's gonna write a specific custom GDB init with a single instruction, source a GDB init script, and this GDB init script will modify GDB to add extra functionalities. Now, after you install the GDB extension, which I have here in my virtual machine, so GDB init, notice that it says source GDB init and a bunch of other configuration here. We can just use it. Here I'm gonna use it on a simple vulnerable program vulnerable to a buffer overflow. So I just do the normal GDB-Q vulnerable, but now essentially it changed and now I have Pwndbg. So with Pwndbg, what I can do is, if I say for example this as main, it's still gonna give me the stuff as before. Now in this case, let's do to enable, let's see, so like this is the program we're working with. It's a simple program vulnerable to a buffer overflow. So I want to disassemble the vulnerable, vulnerable, and I want to put a breakpoint in vulnerable plus 35, which is the line that it calls the string copy. Perfect, I can just do to disable, and then I can do run. But in this case, it says run inferior with, like it doesn't really do anything. Why? Because if I just check the main, disassemble source main, here essentially in main, here there is the intro, here there is a check if argc is greater than 1. So I need to give it an argument. To give it an argument, I can just say run, and then the argument I want to give it. This is equal to execute the program like as follows, vulnerable a, like this. So I do run a, and now I got into the breakpoint, and notice now that it's different. So like Pwndbg comes in and changes the look and feel of GDB. So for example, here I have a lot of information already. I have information about the assembly code up here. So like here, I have information about the assembly code. I have information about the source code. I have information about the stack and the backtrace. So all the stack trace that brought me there. And so essentially this is it for this video. Here in the description I put a bunch of references of reference cards, of Stack Overflow questions on most useful GDB commands and so on and so forth. I mean, GDB is an extremely complex tool with a lot of documentation, and I just suggest you to start using it for specific needs, like you need to debug a program, you need to understand what the program does in a specific scenario, you learn the tools that GDB offers you or that the GDB extension can offer you, and you just use it, learn it, because it is extremely powerful. So as always, that's it for this video. I hope it was interesting. I hope you got something out of it. If you did, please leave some feedback, subscribe to the channel, support here my channel, my growth here on YouTube, share this video with like-minded people, and see you to the next video.